Hey nerds, do you want to learn about fusion rockets? I thought it was time to start celebrating some of the best science in fiction, and is there a better place to start than with The Expanse? Now, there's a whole bunch of topics that I could have picked from the books and from the TV series, but today I want to talk about rockets and fusion. So we're going to cover the Solomon-Epstein drive, and for what should be obvious reasons, you guys, I'm going to refer to it as the Solomon drive or the Rossi rocket for the rest of this episode anyway. Now, what do I mean when I say the best science in fiction? Well, it's kind of subjective, okay? Because I'm not saying that it's the best because it's real or because it will happen. It's just because, in my opinion, it's science fiction done properly, right? Properly doesn't have to mean accurately. It's not like we're going to have the Rocinante exploring the solar system anytime soon. But the best science in fiction is when it's clearly built out of real physics and real ideas, even if it goes to a wild place, so long as it's using what we do know and using it in clever ways to create these futuristic civilizations and bring us these interesting stories. That's enough for me. Hard sci-fi doesn't have to be accurate, it just has to be believable to the story and to us as an audience. And as far as I'm concerned, The Expanse does this. It doesn't try to create a warp drive. There's no faster than light travel, hyperspace, shortcuts through space. Nobody's hopping all the way across the galaxy just to do a job and then being back home in time for dinner. The distances and travel times in the show and in the books are all really important to how the story unfolds. But they do have ships that can travel absurdly fast compared to anything that we can do today. Their crews can accelerate for days, they flip halfway, then they decelerate. Mars, the Belt, the outer planets, all of them are connected in a way that just wouldn't be possible with our current chemical rockets. So how do they do it? The show doesn't get us there by inventing new physics. It gets us there by imagining, well, what if we just got really, really good at fusion propulsion? The Solomon drive is a fusion rocket that can burn continuously for long periods of time with very high exhaust velocity and very high efficiency. Now, it's not realistic in the sense that we could build this tomorrow. We absolutely can't, of course, but they're realistic in the sense that nothing there is breaking known physics. It's engineering, and yeah, it's pushed to the limits here, but it's not magic. So in this video, I want to talk about what makes the Solomon drive such brilliant science fiction. We're going to break down the physics of fusion, look at propulsion, how rockets work, and we'll look at what the Expanse builds its world around and how close, or maybe how far, we really are from being able to build anything like this in our world today. So join me today as we try to figure out how we could maybe build the Expanse's fusion rocket. Now, if you're new here, I'm Abby, I'm a physicist, and I talk about the science of science fiction because I like it, and also because I just think it's a fun way for us to learn and understand about what's really happening in science and in the world of research. So this one is a good one because we've done things warp drive is impossible and teleportation is ridiculous because of all the things that you would need for it. But this is one that we could actually say, hey, maybe we could do this. Like I said, not tomorrow. There's many, many things we would have to achieve before we would get to this kind of a thing. But it's not impossible-ish, sort of. Who knows? I'm making promises here I can't keep, so I'm just going to stop right now. We're just going to move straight back into the episode. To do that, we probably should start with the worst test flight in the history of space travel. Now, in The Expanse, Solomon-Epstein was a Martian engineer who was working with fusion drives that already existed, because fusion engines were not new. Ships had been using them for decades, but they weren't anything like what we see when it actually gets to the show. They were pretty inefficient, they couldn't sustain thrust for very long, so interplanetary travel was still really slow and held back by orbital mechanics. Solomon was working on improving the drive's efficiency. specifically how the exhaust was being accelerated. The existing fusion drives used propellant really inefficiently and they couldn't sustain thrust for very long. Now, he didn't think he was going to reinvent space travel or anything like that. He was just trying to squeeze out just a couple of % improvement, just 5 maybe if he was lucky. So he fitted his prototype to his own second-hand space yacht and he took it out for a test flight. As soon as he engaged the drive, he realized he had made a very, very serious mistake. The thrust he achieved was a lot higher than expected, high enough that the acceleration pinned him into his seat. Now, he tried to reach the controls to shut the engine down, but he couldn't move because the force of that acceleration was too strong. The harder the drive pushed, the harder he was pressed back into his seat. So the ship kept accelerating. Solomon died in his chair, crushed by the sustained acceleration of his own engine as his yacht burned out of the inner solar system. Now, in the timeline of the story, Solomon's yacht is still out there. It's still coasting, still moving at a significant fraction of the speed of light, carrying his body into interstellar space. But the data from that flight, well, that was back home, and that created the Expanse. Once Solomon's notes were released, the design was refined, controlled, and scaled up. Ships could now accelerate continuously for days or weeks. Travel times across the solar system shrunk down. Mars could operate independently of Earth. People moved out into the belts. The outer planets were suddenly reachable, all thanks to advancing fusion propulsion. Now, before we get into exactly what's going on in the Expanse, or what we think is going on in the Expanse, we need to know what makes a good rocket. You see, rockets don't work the way that you might think. Like, the key isn't power here, it's exhaust velocity. At a pretty basic level, a rocket works by conservation of momentum. You throw mass one way and the ship moves the other way. You're not pushing against anything. That might be a misconception. The rocket isn't pushing against the ground. The only thing it's interacting with is its own exhaust. So the question isn't like, how much energy do I have in my ship? It's how fast can I throw stuff away from me? And that speed is called the exhaust velocity, and it's probably the single most important number in rocket design. So every rocket is governed by the rocket equation. It tells you how your final velocity relates to your exhaust velocity and to how much fuel you burned. Now, the relationship is logarithmic. So if your exhaust velocity is low, you're going to need enormous amounts of fuel to go fast. If your exhaust velocity is high, you're going to need a lot less. The equation doesn't scale linearly. That's what's important here, because doubling your fuel doesn't double your performance. You get diminishing returns. Once your exhaust velocity is fixed, adding more fuel mostly just adds more mass, and you now have to push that added mass. That's why rockets leaving Earth are mostly fuel with teeny tiny payloads. Now, we can get exhaust velocity in two ways. They kind of pull in opposite directions. Option number one, throw a lot of mass out slowly. That gives you a really high thrust, like lots of force pushing the rocket forward. And chemical rockets use this. They burn enormous amounts of propellant and throw it out at a few kilometers per second. Well, I say slowly, it's relative. The thrust here is huge, which is what you need to fight gravity and get it off the planet. But once you're in space, you're just burning through propellant really fast because your exhaust velocity is low. So going faster means you need exponentially more fuel. Option number two then is you throw a little bit of mass out, but very, very fast. That gives you a high exhaust velocity, which is much better fuel efficiency, but it's low thrust. Now, electric propulsion like ion drives uses this. They accelerate teeny tiny amounts of propellant to tens of kilometers per second. The thing is, ion drives produce millinewtons of force. Like, that's the weight of a sheet of paper just like pressing on your hand. And you can't launch anything off the planet with that. But if you're already in space and you have months to accelerate, then you'll barely use any propellant at all. So there's a trade-off. You can have high thrust for launch, or high efficiency for deep space, chemical rockets or ion drives. That's the problem that the Expanse solved. If you want ships that can accelerate for days and allow crews to feel gravity from thrust with travel times measured in weeks instead of years, then you need both things. You need high thrust and high efficiency, and fusion propulsion can, in principle, give you both. The Expanse uses this to give its ship's engines with incredibly high exhaust velocity, exhaust moving at a few percent the speed of light. So what makes fusion better? Well, chemical rockets work by rearranging electrons. You take a fuel and an oxidizer, you let them react, and then use the energy to heat a gas and throw it out the back. The electrons that hold molecules together can only release so much energy when they rearrange. So that caps the exhaust velocity at about 4 or 5 kilometers per second. Now, you can absolutely optimize this. You can work on the nozzle, you can tweak the mixture, you can raise the chamber pressure, but you're always going to be near that ceiling. If you want to go faster with a chemical rocket, you have to add more fuel. But adding the fuel adds mass, which means you need even more fuel to push the new added mass. Chemical rockets end up as these towering stacks where most of the structure is just fuel tanks. Nuclear reactions, on the other hand, they don't rearrange electrons. They change the nucleus itself. You force atomic nuclei together or apart, and in the process they release energy and other particles. The energy comes from the binding energy curve. Now, not all nuclei are equally stable. Iron 56 is the most tightly bound, so we can move up and down the curve towards iron 56. Each direction is a different type of nuclear reaction. So heavy nuclei, something like uranium, they're less tightly bound than iron. So when you split them apart into lighter atoms, that's fission, the process that powers nuclear reactors around the world. Lighter nuclei then, like hydrogen and helium, are also less tightly bound than iron. Fusion takes the lightest nuclei in the universe and under extreme pressures and temperatures forces them to overcome their natural repulsion and merge into a heavier nucleus, releasing energy in the process. The amount of energy released per kilogram is millions of times greater than any chemical reaction. But for rockets, the energy density isn't really what matters most here. It's the form the energy takes. In a chemical rocket, energy heats a gas, neutral molecules bouncing all around the place. Now, all you can do is just let that gas expand through a nozzle, and then the exhaust velocity is limited by how hot the gas can get before your engine melts and by the mass of the molecules themselves. Fusion doesn't produce a normal gas. At fusion temperatures, which are tens to hundreds of millions of degrees, atoms can't stay intact. Electrons are stripped off nuclei, so what you get is a plasma, which is free nuclei and free electrons floating around the place, moving independently of each other. It's what we refer to as the fourth state of matter. Now, the sun is a plasma. Most of the visible universe is plasma. Here on Earth, lightning is a plasma. Gas particles are electrically neutral. You control them with walls and pressure, but plasma particles are charged. Ions and electrons, they respond directly to electric and magnetic fields. So you can guide them, confine them, accelerate them without ever physically touching them. In many fusion reactions, especially the ones that would be useful for propulsion, a lot of the energy ends up in charged particles. So things like protons, helium nuclei, fast-moving ions, they all come out of that reaction already traveling at thousands to tens of thousands of kilometers per second. So you're no longer limited to heating a propellant and then hoping it expands. You have charged particles moving at a few percent the speed of light, and you can steer them with magnetic fields. So you can take the kinetic energy of the fusion products themselves and turn it straight into an exhaust. Comparing the exhaust velocities for what we've already talked about, chemical rockets, about 4 to 5 kilometers per second. Ion drives about 20 to 50 kilometers per second. Fusion products come out at about 10,000 to 30,000 kilometers per second. At these velocities, you don't need to be mostly fuel. You can burn continuously for long periods without throwing away your entire vehicle. So what does this mean for the Expanse? Well, okay, the Expanse doesn't give us like a complete technical manual for how the Solomon drive works, but we do know a few key things from the books and the show, so we can kind of try to figure out what we think is going on. We know it's fusion powered. We know that it uses water as propellant. That's the reaction mass that gets expelled at enormous speeds. We know that there's a magnetic bottle mentioned that confines the reaction. And we know that Solomon's breakthrough was in how efficiently the exhaust is accelerated. Now, the result is exhaust velocities at several percent the speed of light. That's enough for us to understand the basics of what they might be doing. They're using fusion energy to superheat water and accelerate it to enormous speeds. The fusion provides the energy and the heat, the water provides the mass, and then you throw it out the back. The breakthrough that made Solomon's design revolutionary was maybe something to do with how efficiently the energy is getting transferred to the water propellant, or how well the magnetic fields are accelerating that superheated plasma out the back of the rocket. So they're essentially using fusion as a furnace. The reaction creates the extreme temperatures. Those heat the water that's injected into the reaction chamber. The magnetic fields then guide that accelerated superheated plasma out as the exhaust. This is speculative. Like I said, the Expanse doesn't give us any blueprints. They haven't said that this is what's going on, but it fits what's described and it uses physics that we understand. The principles are real. The engineering, it's really, really hard, you guys. Now, there are a lot of different ways that you can approach creating fusion reactions, but there are two main ones that are dominant, I guess. Firstly, we have magnetic confinement. This uses shaped magnetic fields to trap plasma. Charged particles then spiral along the magnetic field lines, so you can use the fields as invisible walls. So on Earth, these are things like tokamaks and stellarators. They create closed magnetic loops where plasma circulates, never touching the physical walls of the instrument. The goal is to trap it there long enough to sustain fusion and then extract the energy as heat. The other method most commonly used is inertial confinement. This compresses fuel so quickly that fusion happens before the fuel has time to fly apart. You can use lasers, particle beams, pulse magnetic fields to crush the teeny tiny fuel pellet, the size of like a little peppercorn, from all sides simultaneously. And the compression heats it up to fusion temperatures for just a brief moment, but it's long enough for nuclei to fuse and then release the energy. Now, based on what the Expanse describes, laser-ignited fusion, a magnetic bottle, water as propellant, here is a plausible mechanism. Not saying that this is what it is. This is just what I think it is based on what I have inferred from the show and information that I have found online. Okay, here we go. We start with inertial confinement. A fuel pellet gets injected into the reaction chamber and it's compressed by converging lasers. We know this happens because they showed it to us. The pellet implodes, heating to fusion temperatures, and then fuses in a controlled burst. This happens really rapidly. Think of it like a pulsed engine, firing repeatedly rather than burning continuously. Now, each fusion pulse produces a burst of extremely hot plasma, charged particles and radiation moving at enormous speeds. That's where the magnetic bottle comes in. Now, instead of letting that energy disperse, magnetic fields surround the reaction chamber and trap the plasma, confining it temporarily. Next, you need to inject water into that magnetically confined plasma. The water instantly vaporizes and ionizes, becoming part of the plasma. The fusion energy heats it to extreme temperatures, and so you've turned the fusion reaction into a furnace that is superheating your water propellant. Finally then, the magnetic field opens at one end. This is a magnetic nozzle. The field geometry guides the superheated plasma outward in a directed stream. The charged particles follow the field lines accelerating as they do. The geometry matters here. If it's too narrow, then you'll have like turbulence disrupting the flow. If it's too wide, then the exhaust will like spread out instead of pushing straight back. But if you get it right, and if you direct most of that fusion energy into a tight, fast exhaust beam. This is speculative. I've said this a million times. We're inferring from very limited details here, you guys. But it combines very real physics in a way that matches what the Expanse describes. Pulsed inertial fusion for ignition, magnetic confinement to control the reaction, water as propellant to provide the mass, and then magnetic acceleration to achieve extreme exhaust velocities. I love it. I think it's brilliant. This is what I love doing about this kind of stuff, you guys. It's not always about what's right. It's about like, can we look at it and can we figure it out? Can we find a way to go like, oh, we could maybe do that. And here's all the things that we could do to do that. It's really exciting. I might need to calm down. I like talking about rockets. And I guess technically I'm a plasma physicist. I mean, my research is centered around Wakefield acceleration, but my supervisor is very much an expert when it comes to inertial confinement fusion. So if I've gotten anything wrong in this is going to be very disappointing. Now that mechanism I described, pulsed inertial fusion with magnetic confinement and acceleration, like I said, it's using real physics, but each piece comes with enormous engineering challenges. Achieving inertial confinement fusion is the first one. Now we have achieved fusion through this method, but like only kind of just. In December 2022, the National Ignition Facility achieved fusion ignition. That's when you have more energy coming out than the laser puts into the fuel pellet. This is a major milestone and it's really exciting. But there is like a distinction here that explains why we're not currently using it for fusion energy. The energy out exceeded the energy delivered to the target, but not the total energy needed to power the entire system, the lasers, because lasers are inefficient. You put in orders of magnitude more energy than reaches the fuel. So for the National Ignition Facility, overall, the system energy balance is still really negative. For a rocket, you need to be able to do this repeatedly, like many times per second with extremely efficient lasers in a compact system that fits on a spacecraft. So when I say we're nowhere near to doing that, yeah, come on guys. The other thing is about the fuel choice and radiation effects. You see, the easiest fusion reaction to achieve is deuterium-tritium. We can heat that to about 100 million degrees and it will fuse, releasing energy. But about 80% of that energy comes out as neutrons. Now, neutrons are uncharged. That means that magnetic fields can't control them. So they just like fly off straight through your engine structure, your propellant tanks, your crew compartment, and they cause radiation damage and activate materials making them radioactive. So for a power plant on Earth, you can use those neutrons to heat water and drive turbines. But for a rocket, that's a little bit more of a problem. You can't direct them into the thrust and they damage everything they touch. So what you'd prefer would be something like a deuterium-helium-3 fusion reaction, because when they fuse, almost all of the energy goes into charged particles. You get a helium nucleus and you get a proton. Both of them can be guided magnetically. Less than 5% of the energy ends up in neutrons from side reactions. The problem is that deuterium-helium-3 needs much higher temperatures and much better confinement than the standard deuterium-tritium. So it's significantly harder to achieve. And helium-3 is extremely rare on Earth. Like there's barely any in our atmosphere or the crust. Now the Expanse can solve this because they can just mine helium-3 from like a gas giant atmosphere. That's speculative, but it's not impossible because gas giants like Jupiter and Saturn do have helium-3 in their atmospheres. So if you're stuck with deuterium-tritium fusion, you're going to need really heavy shielding to protect the crew and the systems, and that adds mass, which fights against everything that you're trying to achieve with the high exhaust velocity. Deuterium-helium-3 would be much better for propulsion, but it's also much harder to achieve. Now, another thing is the heat problem, and this might be the hardest challenge because no engine is perfectly efficient. Fusion reactions produce enormous amounts of energy, and some fraction of that becomes waste heat. Now, in the Expanse, ships don't have massive radiator arrays. Like the Rocinante doesn't have any visible heat management system that we can see. But the laws of thermodynamics don't really care about the aesthetics of your spaceship. If you're running a fusion engine producing terawatts of power, even if you're like 90% efficient at converting that into thrust, you still have hundreds of megawatts to gigawatts of waste heat. And in space, the only way to get rid of heat is through radiation, like glowing it away as infrared light. That requires really large surface areas. So we can just say, look, it's science fiction. Either it has an incredibly efficient heat management system that we just don't know how to build and we haven't seen it yet, or it's just one of the things that they just went, we're just not going to think about that. It's fine. Given how carefully they handle like most of the things within the story, we can just say some things we assume that they have solved. But we don't know how they're technically solving it in the show. Now, once you're off the Earth, the requirements change. You're not fighting gravity anymore, so you don't need massive thrust. What matters there is efficiency, being able to change your velocity without burning through all of your propellant. So one of the best ways to do that right now is electric propulsion. Most spacecraft today use this method. They have ion drives and hall thrusters. These both work by ionizing the propellant, which is either xenon or krypton, and then accelerating those charged particles through electric fields. The exhaust velocities are really high. It's 20 to 50 kilometers per second, about 10 times better than chemical rockets. It's really similar to what we've just talked about with the idea of the fusion reaction. It's just that it has an external power source to provide the electricity to do the process instead of the fusion reaction. But a rocket like this is the reason why NASA's Dawn spacecraft was able to visit both Vesta and Ceres on a fraction of the fuel that a chemical mission would have needed. It's also why there are thousands of Starlink satellites using hall thrusters for station keeping. But like we said, the thrust is tiny, millinewtons, the weight of a sheet of paper. You need months to build up speed, so you can't accelerate at like 1G. You're not going to like flip and decelerate. Travel times are still going to be in years, not weeks. But something that has been on the books for a while is VASIMIR, the Variable Specific Impulse Magnetoplasma Rocket. Now, this has been tested extensively in vacuum chambers on the ground, but it has never flown in space. It uses radio waves to heat propellant into plasma, then magnetic fields to accelerate it. The concept is proven in lab conditions. It produces a measurable thrust, and you can adjust the exhaust velocity on the fly, which is really cool. So you can trade off thrust and efficiency when you need it. But it needs hundreds of kilowatts of external power, which is a lot more than most spacecraft have available. And without that power source, it's just going to remain a ground demonstration. Now, these systems are limited by, like I said, that need for external power. Solar panels or a nuclear reactor to generate the electricity, which then accelerates the propellant. So that limits how much thrust you can produce. Fusion is different. The energy comes from the fuel itself. You're not accelerating propellant with external power. You're using fusion energy to superheat the propellant directly. So if it sounds like it's such a great idea, is anyone actually working on it? Well, kind of. Some groups are working on concepts that combine these elements. Now, Princeton Plasma Physics Lab has proposed direct fusion drives using magnetic nozzles, and companies like Helion Energy and General Fusion are attempting to develop fusion systems for power generation that could, in principle, inform propulsion designs. There's this other one that's I've seen a lot about recently, which is pulsar fusion in the UK, and they say that they are explicitly working on a fusion rocket engine. They have built test chambers and they are working towards prototypes. The problem is, because it's industry, their work isn't publicly documented, so we don't actually know where they're at in their design of their system or if it works. None of these are flight ready. They're all early stage research, but they're attacking the same problems. Achieving fusion in a compact system, controlling it magnetically, and directing the energy efficiently. So we have the pieces. We have inertial confinement fusion. We have magnetic confinement. We have magnetic nozzles. We know that they work in low power plasma thrusters. What we haven't done is integrated them into a compact, high power system that can fire continuously, manage enormous waste heat, and fit on a spacecraft. Like I said, this is not a one-year problem. It is decades of work if the inclination is there. But the physics is real and the pieces are all being worked on individually for other reasons. The main one being that we want fusion energy here on Earth. We don't technically need to do anything different other than support what is currently happening in fusion and plasma research, because developing all of these different methods is what will allow us to get better, more efficient, and more compact versions of this type of technology in the future. There's this joke constantly that, like, you know, fusion is like 20 years away, but like fusion probably is about 20 years away. It's a big challenge. It's not easy defining these geometries or building these systems and confining things that are so hot and so fast and have so much energy in them. We have to do it safely. So ensuring that all of that is done really safely on Earth before we can then figure out how we could put that in something that we're going to put up into the sky, pretty important, you know, with anything. So the Expanse gives us fusion rockets, and then it imagines what our solar system would look like if we could haul people and resources between planets at a fraction of the speed of light. The Solomon Drive, it's a long way away, like if we were to ever build something like that at all. But the Expanse took something that, while it's speculative, it is very real physics and very plausible engineering, and then it created a world and a story around it. And that, to me, is what makes it some of the best science in fiction. But I want to know what you think. Do you agree with me? Do you love the Expanse? Do you think it's a clever idea? Do you think that this is something that we could build? Or are you still just kind of in that, like, nah, I don't think fusion's ever going to work? I mean, we know it works, you guys. It's just that there's still a lot of stuff that needs to be done with it. Let me know anyway in the comments what you think about this in general. Now, as per usual, I will be breaking this episode down into a series of shorts where I can do a bit of a deeper dive on some of the specific topics, looking at like the maths, the plasma physics, the propulsion concepts. And for Patreon supporters, if you're interested, I'm thinking that I might do an in-depth look at nuclear thermal propulsion. So like fission and why it worked in the 60s, but why we don't actually use it. And also why attempts to bring it back just seem to keep failing. Anyway, thanks for watching. Stay nerdy.